In this demonstration, we will discover and discuss the relationship between angles that an arrow is fired at and its velocity, trajectory, and distance that it travels on the x and y axes. We'll also look at the experiment in context of Newton's laws of motion. In order to understand the experiment, we must first understand what a projectile is, that being an object subject only to the force of gravity. For any projectile, Newton's laws of motion are relevant. The first law is that an object that is in motion can stay in motion unless it is acted upon by an outside force. In context of this experiment, the arrow will continue to move upward until the downward acceleration due to gravity negates the initial upward velocity. The arrow then moves down the y-axis until it comes to rest on the ground. The second law is that the direction of an object's force vector and acceleration vector are the same. For example, its resultant forces, or the sum of two or more forces, will end up in the positive x direction, the same way the arrow accelerates when it is shot. The third law is that for every action there is an equal and opposite reaction. In context of the experiment, this law can be described in context of the parabolic graphs that you will see. The distance that an arrow spends on an upward trajectory of the y maximum of the parabola is the same distance that it spends on a downward trajectory after the y maximum. When an arrow is projected from a bow, its motion has two components, one horizontal and one vertical. Air friction will be ignored. To calculate the horizontal distance that the arrow traveled, we use the equation delta x equals v sub x times t. To calculate vertical distance, we use the equation delta v equals v sub x times t, minus 1/2 the acceleration due to gravity times time squared, plus the initial height that the bow was fired at. To find the velocities of the unknown size, we use some trig. We use the equation sine theta equals opposite over hypotenuse, or vy over v, and the equations cosine theta equals the adjacent over the hypotenuse, or vx over v. The overall formula used was that the distance equals v naught squared divided by the acceleration due to gravity times the sine of 2 theta. And to find the velocity, we use the equation the square root of the distance times the acceleration due to gravity over the sine of 2 theta. First, let's have a look at our data. The graph currently on the screen shows the average trajectory for each angle at which the 3 arrows are fired. As the angle increases, so is the distance delta x, the arrows having more airtime at a constant x velocity. For safety reasons, the velocity and trajectory of the 90-degree angle were estimated, not tested. Velocities the arrows gained are a result of the force that was applied to the arrow when it was fired from the bow. Velocity is calculated using the formula v equals delta x over t. As the force that the bow applied to the arrow never changed during testing, velocities of all the tests are the same. Before we delve into data analysis, I must establish our assumptions. First, that air resistance is a negligible factor. Second is that gravity is the only force acting upon the arrow after it exits the bow. Third is that the resulting experiment only applies to specific bow and arrows that were tested. All the arrows were altered in the same fashion in order to accurately represent angles to distance ratios. The data collected indicates that in order to get an arrow to cover the most distance, it must be shot at a 45-degree angle. The reason this result is correct can be found when looking at the graphs of an arrow's trajectory with the knowledge that a projectile flies in a parabolic motion. For example, if one fires an arrow at a 0-degree angle, the projectile starts traveling from its y maximum. This means that with no upward velocity, the arrow quickly falls to the ground. On the other hand, the 90-degree firing angle produces the maximum y displacement from the bow with the lowest x displacement. The initial velocity is slowly cancelled out by the acceleration of gravity. The arrow moves slower and slower until reaching a point where it has no velocity at all in the y direction. Velocity then increases in the y direction as gravity pulls the arrow back to Earth. The reason that an object begins to come downward is due to the acceleration that a projectile has in the y direction due to forces applied to it can only last as long as the acceleration the object experienced due to whichever force moved it is greater than the acceleration due to gravity. The distance traveled in the x direction is proportional to the distance traveled in the y direction. When the arrow moves upward at a sharp angle, increasing its distance in the y direction, it will not move very far in the x direction and vice versa. Thus, the angle that is in the middle of the two extremes, 45 degrees, the ideal angle to shoot an arrow for the short to cover the farthest distance. In the x direction, the 45-degree angle illustrated by the green bar travels the farthest distance, while the 90-degree angle that travels the shortest distance, followed by the 0-degree angle as the second shortest because it only takes advantage of half the parabolic motion the arrow travels in. Position versus time graph in the y direction also verifies the idea that a 45-degree angle is the middle ground between accelerations in the x and y direction, as it hits the middle height in all the tests, while the 0-degree angle reaches the lowest maximum and the 90-degree angle reaches the highest maximum, due to their having the steepest and smallest parabolic motions respectively.